How's everyone today? Cool. All right. Go ahead and send me an attendance note, please. All right. Well, PA5 is done. All PA5s that are being turned in have been turned in and graded, and grades posted with feedback. And so let me start off by just doing a quick run through on my version of PA5, just to give you a different view of an approach to this. So most people got this working, at least, for the most part. Maybe tripped up a little on test 3 or test 4, but mostly this seemed to work for people. So this is a version that's based very strongly on the way the assignment was written and the suggestions we've gone through in class on how to break the input and process it and so on. So shebang always has to be the first line of the file. And I noticed some people, got their program written, finished, everything's working, and then went in to add comments, and in some cases put those comments before the shebang. And if you have other stuff before this is no longer doing anything, it's just a comment. It's only if it's the very first line of the file that it's treated as, an instruction for how to run the file. So make sure that's always the first line. And then, you want some kind of intro that, lists your name, the date, the name of the program, and then some sort of synopsis of it. And depending on who you're turning this into, your synopsis can have, more or less detail. But this is probably a minimum level of detail. Read standard in, cleanse the input, break it into phrases, tally the phrases, output final tally after end of file. And then, what do we mean by cleaning? What do we mean by a phrase? But, this could be a lot more detailed. The assignment prompt is 4 pages. You could certainly have a lot more information in here. And if you were putting this into a library somewhere where other people would be using it, or if you were going to refer back to it, a year from now, you would want all this information in here so that you don't have to sort through the code and say, so what separates one phrase from another? And you have to, dig it out of the code, right? So I would list, what are these certain punctuation marks? What are these special characters that we remove, and so on and so forth. And it's not uncommon if you start downloading software and trying to build, packages from it, that you might find, 500 lines of comments and, 10 lines of code. And that's not unusual to have, a lot more intro comments than you actually have code, because these intros get shared from module to module and so on and so forth. All right, so declare your associative array somewhere in the beginning outside of all the looping. And then here's my main input loop. So while read line do, and that's going to take me down to here. So when I come out of this loop, I've read all of the input. And the way this is set up, as you're reading the input one line at a time, you're cleaning, breaking into phrases, tallying. Read the next line, clean, break into phrases, tally. Read the next line, clean it, break it into phrases, tally those phrases. And so when we're done with that loop, then we're going to go into a final loop where we output the results of the tally. So this reads one line, everything up to a new line, and it stores that line in this variable called line. So clean up the line. So echo the line and put that into TR. Now if you don't do this, then TR will read from standard in. And if you don't do a read line and you just start with a TR, your program will look like it's working, but it's really reading the entire input all the way up to the end of the file, not just the end of the line, and then turning that into a variable. So here we're taking one line in from the user, we're echoing that line and sending that to the standard input of TR, so that converts case. This changes special characters to an @ symbol, this changes quotation mark to an @ symbol, this is a continuation. This gets rid of the @ symbols, so now we've cleaned out all those special characters. This changes spaces and tabs into underscores, and this changes multiple consecutive underscores into a single underscore. So we've cleansed the input, we've converted it to uppercase, gotten rid of special characters, compressed multiple spaces into a single space, and changed those into underscores. And now we're going to take all the possible separators and change them into a single space. So that's one sed command. Or you could do it as multiple commands, but I basically echo the line, which is cleaned up, and I substitute all these separators with a single space. And I call that variable phrases. So phrases is a set of space-separated phrases where each phrase has underscores instead of spaces. So now I can for phrase in phrases to iterate over each of those phrases, and phrase will be the next phrase I'm processing, and my goal now is to tally it. So first thing is get rid of leading and trailing spaces, so change caret, the anchor at the beginning, followed by any number of underscores, just get rid of those. And any number of underscores followed by the $, which is the anchor at the end, get rid of those. And then here's this check to see if we're left with an empty phrase, which could happen if I say, you know, comma, space, comma, that will come out as an empty phrase. So if my phrase is empty, then we just continue back up to the top of this loop. Alright, otherwise, what do? Read the current count. So the whole game here is count is an array which is telling us how many times each phrase is stored. If we want to know how many times a phrase appeared, we just look at that element of the array. So if we want to know how many times phrase appeared, count bracket phrase will tell us that number. And this will either be an integer or it will be a blank. We increment it, and then we save it back into the associative array so that the next time we use this phrase, it'll say, oh, you've seen it this many times. And so that's our main marching across this one line of phrases and tallying them. And then this is the end of the input loop, so this part processes a single input line. This loop up to the top processes the entire set of input lines. And when we get down to here, we've hit the end of file on the input, we've kicked out of that main while loop, and now count is our tally of all of our phrases. So we do one more for in loop, and we iterate over the keys, which are the phrases, and for each one, phrase will be the phrase that we've seen, so this will be the number of times we've seen it, and we take the phrase, we change the underscores back into spaces, and we output that. And that gives us our nice tallied output. So main takeaways to know here for the final exam, right? Know how to do this while read loop so that we can keep reading one line at a time and detect end of file. Know how to set up an associative array. Know how to use an associative array, so when you want to read from an array, you use this funny notation, $, curly bracket, array, bracket, index, close bracket, close curly. If you don't have those curlies, bad things happen. And then this is how we increment a variable in bash. We learned that in the beginning of the term, and this is how we write something into the array with a certain index. We don't need the curlies here, but we need them here. And so if you tried to do this in one line and you used this syntax instead of that syntax, you got potentially strange results or strange treatments of $signs and things like that. And I'm a fan of breaking things into pieces if there's any possibility of confusion, right? We could do something like, count bracket $ phrase equals $ $, curly bracket count bracket quote phrase quote bracket curly bracket +1 paren, right? There's so much potential for syntax error in here, and even worse, there's potential for a semantic error that doesn't give you a syntax error, that goes ahead and runs normally but doesn't do what you want it to do. And maybe when you're done, your counts all come out to be 1. And it's because, you know, you forgot a curly bracket in here, or you forgot quotes around phrase, or something, you know, and you're debugging some other part of your script because you think that's where the error is, and it's really just this, right? Make life easy on yourself, right? Break things into pieces. And if something goes wrong here, it's easy to debug, right? C is the count bracket phrase. Right here, I can put an echo statement that says, hey, show me what phrase is, show me what C is. And I can see, you know, do those have the right value? And then right here, after C equals C plus 1, print out the new value of C. If up here it told me that C was equal to 0, and down here it tells me that C is still equal to 0, I got some kind of error in this statement. And then, you know, after I make this assignment statement, maybe I'll go ahead and I'll echo the new value of count bracket phrase and make sure that took. And if it didn't, I did something wrong in here. Maybe I said phrases instead of phrase. Right? But the smaller the piece is, the easier it is to sort of dig around in between each piece and try to figure out where something's going wrong. So make life easier on yourselves when you're coding. And you know, after you're done with this, if you want to try to turn these 3 things into a single statement, cool, go for it, you know. But at least you know that all of this stuff is working, and if when you change this into one statement it doesn't work, you know there's something in that statement that you need to dig into. This part up here where I'm taking the line, I'm echoing it, I'm doing a translation, a translation, a translation, and a said, and the translation, and the said. You could do that in 6 or 7 different steps. And then print out the results after each piece of this and see, you know, oh, I did something wrong here. I forgot to put my quote, and it changed my entire line into, you know, @ symbols or something. And the only thing I grade is, you know, your final submission. So feel free to like change the problem, do subsets, do simplified versions of the problem, put in debug statements, all of that. That's all going to help you with debugging. All right, so any final questions, comments, reflections on PA5? All right, so let's continue talking about processes. And we were playing around with these sleep commands yesterday. And so if I say sleep 1000, I have a process that's, you know, hanging out sleeping. And if I go into a different window and I do a PS, right, I don't see that sleep process. The reason being that this is showing me processes associated with this particular terminal session, this window. So there's options I can put on PS to get more information out. One option is PS-L. And PS-L shows me a longer view of my processes. So I've still got the command and the time and the terminal, but I've also got some information about the size of the process. I've got its priority or its niceness values. I have its process ID, but I also have its parent's process ID. I have a numeric ID for who owns the process, and the current state of the process. And my PS command is in a running state. And bash, which was my command line, is sleeping right now. PS is running because that's what generated this. Will Linux processes be part of the final? Definitely. Yeah, it's like a tenth of the course, so it'll definitely be on there. All right, so I can do a PS-L, get a longer view of what's going on. I can do a PS-F, and I can see now my entire command. Instead of just bash, I can see that this was /bin/bash. Instead of just PS, I can see that I'm running PS-F. And I don't expect you to memorize these. I don't expect you to, answer a question. What does PS-L do, right? Because we can look that up. But I want you to understand basic concepts of processes. The fact that we can run something in the background by saying Control-Z. We can bring it to the foreground with FG. Stuff like that. So you'd probably see like conceptual questions rather than very highly detailed questions. Alright, if I do a PS-E, that shows me all the processes on the system, whether or not they're owned by me or by somebody else. And there's a lot of processes on most Unix systems. And so a lot of these are owned by root, some of them are owned by me. So if I do PS-EF, I can get even more information, and these jobs that say root, these are system processes. These ones that say Nick, these are my processes. There's my Zoom processes. Here's my terminals. Here's some bash shells I have running. Here's the screen recorder that's making the video that gets posted later. Here's the document camera. Right, it's doing a 1600 by 1200 resolution on my Video 2 device. That's, the document cam, and so on and so forth. There's my mail client running in the background. So you can find out a lot about what's going on the system using this PS command. And so the one I tend to use most often is PS-elf, and that gives me a long view with lots of information. But if I look through here, I'll find this sleep 1000 command. Depending on how good our image recognition is, there it is right there. So that's Nick running a sleep 1000. The command started at 11:14, which was about 4 or 5 minutes ago. But you could also pipe this into grep sleep and find the command like that. But I can also say PS-user Nick and ask to see all the processes owned by Nick. And so, these are all the things that I'm running or that are running in this other window, including sleep, or things that, I've got running from whenever. All right, so PS is a useful command. And if I Control-Z this and I do a PS over here, I can see my sleep command was 9702. Well, that's the same thing we found over here. Process 9702 running on PTS1 terminal 1, right? That's this sleep command. And if I kill it, it goes away. All right. So, I say sleep 1000, I hit Control-C, and it kills the sleep command. And I think I mentioned yesterday that Control-C does not actually immediately kill a process. What Control-C does is it sends a message to a process. And it sends a message with a funny name. The name of the message is SIGINT. And if I've got a process running right now under bash and I hold down Control and press C, I'm asking the system to send a SIGINT message to the current process, sleep 1000. And that's all that Control-C does. It doesn't somehow go out and actually kill the process. It just sends a message to it. But the sleep command is set up so that when it gets a SIGINT message, it exits. But we can change what a process does when it gets a signal. So there's a variety of signals that we can send to messages. SIGINT is signal 2. And it's the signal that's generated when we hit Control C. SIGSTOP is signal 20. That's what's generated, sorry, signal 19. That's what's generated when we hit a Control Z. SIG8 is SIG-FPE. That's what's generated when our process tries to do something illegal with arithmetic. If we try to divide a number by 0, the floating point system in the CPU will cause a SIG-FPE signal to be sent to the process, telling the process, hey, you had an FPE, a floating point exception. If we try to access a location in memory that doesn't exist, the memory management system will cause a signal 11 to be sent to the process. That's SIG, segmentation violation. That's a seg fault. So these different signals are the ways that processes or hardware talk to one another. And sometimes a process sends a signal to another process. Sometimes a piece of hardware causes a signal to be sent to a process. And so, for example, if I say sleep $1,000, and let me all right, so that's process 10349. I can send a message to this process by using the kill command. And the way kill works is you say kill space and then the number of the signal you want to send. So I could send, for example, a sig stop message. So I could say kill 19 10394, and this process is terminated. Oh, that's interesting. That was a bit of a snafu. I can't stop it from another process group. All right, so let's kill it with something interesting. Let's send a sig FPE. So let's do a kill 8 on 10422. Okay, fine. Let me just kill it myself. So let's do a kill dash 8 10437. And my process exits, but it exits with the message floating point exception. Right? There was no floating point exception. It's not that sleep did something illegal with arithmetic, but it got a signal 8, which is sig floating point exception. And so it thinks that, you know, something went wrong with an arithmetic operation, and it printed out this message, floating point exception, and then exited. If I send it a 19, it tells me that it stopped. And it looks now as if I had hit a Control Z to put this process in a stopped state. And I can say BG, and it'll keep running in the background now. If I kill it with a signal 11, that's sig seg v, segmentation violation. My sleep process says seg fault. We didn't actually cause a seg fault. There was no memory access being made. There was no illegal memory access being made. But the process doesn't know that. All it knows is it got this signal 11, and it's been written so that when it gets a signal 11, it says, oh, there's a seg fault. But if you have a piece of C code and, you know, you use a string that you didn't allocate memory for, and you try to do a string length on it and you get a seg fault, what's happening is the memory system is saying, oh, this is an illegal location, it tells the operating system that. The operating system sends a signal 11 to your process, and your process says sig fault. So signaling is the main way that processes communicate with each other inside the system, at least at a first level. But you could have a signal, for example, you could set up a user signal like SIG_user1 that says, hey, if you get this signal, go look in this file for information. Or open up this pipe and start reading instructions out of there. And so we can use signals to alert a process to some condition that may not mean, you know, stop running. It may mean go do something else. So you can see a list of signals by saying trap-L. But trap is actually a bash command. And with trap, I don't know if we have a man page for it. Yeah, we do. So we can say trap, and we can list a signal, or we can say trap and specify actions we want to have taken when a signal is received. So here's a bash script called sleeper, and it sets up a trap in the beginning which says, hey, if you get signal 2, execute the command print working directory. And then sleeper sleeps for 20 seconds and then says sleeping some more and sleeps 5 seconds and says bye. So if I run this in the background, it's sleeping for 20 seconds. But if I send a signal 2 to it, so kill-2%1, it prints my current working directory, and then it continues on to sleeping some more, and then it says goodbye. So what's happening? It's hanging out in the sleep statement. When I send it a signal 2, it kills the sleep statement, but it also does this command, print working directory in this case, which it printed out here, and then it goes on to the next statement which says echo this message, sleep 5 more seconds, and then say goodbye. So now you can do things like make a program that ignores signal 2. So I'm saying if you get signal 2, echo this message, haha, and the main program is just an infinite loop, prints hello, sleeps for a second. So if I run this in the background, it prints out hello every second. And if I send it a kill message, it just laughs and it continues looping. Well, signal 2 is a sig int. That's the signal that's generated when we hit Control-C. So if I run my sleeper program, I hit Control-C, instead of exiting my script, it prints out my current directory, sleeps 5 more seconds, and says bye. So sleeper 2 prints out hello every second. If I try to Control-C out of it, it just laughs at me. And I cannot terminate this program with Control-C, because Control-C doesn't inherently terminate a program. It just sends a signal, and I've told this script, trap that signal, print out haha, and continue running your program. But I can Control-Z it to stop it, get back to my bash shell, and I can always kill a process with a signal 9. So signal 9 is sig kill, and that means just, you know, kill the process, no questions asked, and you can't trap a signal 9. So if you have a process that you can't get rid of any other way, you can always kill it with a -9. It's a really heavy-handed way to kill a process, though. On some systems, it may leave you with resources that aren't reclaimed. It may leave you with things in sort of a incomplete state, but it will kill a process without hesitation. All right, so that's a little bit about interacting with with processes from Bash. The more interesting part is looking at how these processes actually come into being. So I want to look at process creation from C, because you know Bash is just a big C program, right? So all of this stuff that we're seeing, running things in the background, sending messages with kill and so on, these are all, you know, things that are being done in C. And so process creation is based on a function called fork. And we can look at the manual page for fork. And fork says create a child process. And we have to include it from unistandard.h. But it basically creates a new process by duplicating the calling process. So here's the idea. You have some main program running, doing whatever, and at some point it makes a call to fork. And as a result of that call, a second process is created. And this second process will be an almost exact copy of the first process. It'll be executing the same code, its variables will have the same value, and so on and so forth. So let's mess around with this a bit. So we'll do a fork test. Alright, so I've got a couple of variables here, I and j. I'm going to set those up. I'm going to say ready to call fork, and then I'm going to make a call to fork, and then I'm going to print out the values of I and j after that, and then I'm going to say goodbye. Alright, so pretty simple test code here. Right, so assign two variables, make a call to fork, do a couple of print statements. If we run this, we get something that might be unexpected. It said ready to call fork, and then it printed out I and j and said goodbye, but it did those two things twice. And this is exactly what it should do. So we ran our main program. It made these assignments. That's fine. It said ready to call fork. That's what we saw here. As soon as it made this call to fork, when it finished that function call, we had two copies of our process. And each of them was sitting at the same point in its copy of this code with the same values of the variables. And each of them executed this print statement, printed out I on j. Each of them said goodbye. And then they exited. And this is how processes come into existence on Linux, other than the first process. Every process is basically a clone of some other process. Now, it's not very useful to have a million copies of one process, so usually what happens is down here, after we've made this duplicate, we do something like a call to a function execl, and we use that to change this process into something else. And we'll talk about that tomorrow or Thursday maybe. But for now, I just want to think about this fork function. So fork duplicates the current process. And if I do something like this, Alright, so let's run our program. Let's have the user type something in, save it in this variable buffer, and then we'll call fork, and we'll have each process print out the value of buffer. So I can say this is weird. And, you know, both processes have that variable value now. Both of them have buffer that's been set to this is weird. So this new process and this old process are almost exactly the same. Same variables, same code, same instruction space, but it's a separate process. If I change a variable here after it's forked, it will have no effect on the variables in this original process, and vice versa. They're two independent processes, but this was created by cloning the original. And it's almost an exact clone. But you always want to be able to tell who's the original and who's the clone. So you put the little, you know, dots tattooed inside the eyelid or something, so you can tell who's the clone. So with a fork, the way we can tell the clone is the return value from the call to fork. And so if you look at the manual page down at the bottom, it shows you return values. On success, the PID of the child process is returned to the parent. 0 is returned in the child. And that's the only difference between the two processes, is the value that comes back from the call to fork. So let's print out the return value from fork. And so now we can see one process said p equals 11884. The other process said p equals 0. And that's the only difference. So we can use this to identify ourselves. Let me get rid of this stuff. I guess I had that. So let's just run this process. It's going to say ready to call fork. It'll call fork, and it'll save the return value in a variable. And then each process will execute this if statement, which says if p is 0, print out I'm the child process. Otherwise, print out I'm the parent, my child's PID is p. Each process is going to do this, each process is going to do this. But we're going to change what each process does by using the value of this variable p. So this is state-based code. So if we run this, it says ready to call fork, and then we got two sets of messages coming out. The parent said, I'm the parent, my child's PID is 11984. The child said, I'm the child process. All right, questions so far? This is strange stuff, and again, I'm not expecting you to, like, you know, grok all of the details and so on. I just want to kind of show you this at least once in this course, and you'll definitely deal with this in the university in a lot more detail. Why is the child process execute after the parent? Because I have a single CPU, and if I did enough stuff in here, so let's do something in here. let's put a for loop in here. So if the child figures out it's the child, it'll say I'm the child, and then it'll go through and it'll recite the numbers from 0 to 199. And if it's the parent, it'll say I'm the parent, and then it will go through and recite the numbers from 0 to 199. And if I do this, right, you can see they're taking turns in some spots. The child said 154, the parent said 183, child 155, parent 184, and so on. But in the beginning, right, because I have this check for the parent first, the parent said a bunch of stuff before the child process got to the point where it was ready to say I'm the child. Actually, the child gets tested first. So this gets into process scheduling. And so here, you know, the child kicked in after the parent said 20. If I run this again, I'm going to get something probably totally different. Right? In this case, the parent got up to 8 before the child woke up, and then the parent got to 14, and the child started sharing its turns at that point. And I'm going to get a different result probably each time I run it. So this is asynchronous programming. We have two processes running basically independently. And in general, you know, since it's the main program that's running, this is creating a new process. Well, process creation takes time. There's a lot of overhead that has to be done to create a new process. It's OS scheduling. A whole set of data structures have to be created and manipulated. And so there's a good chance I'm going to get to this part of my main program before the child process starts. But if we do more stuff in here like this, we can see, you know, what's going on. So we can also, let's just throw a sleep statement in here. And let's see what these process IDs look like. And let me run this in the background. So the parent said, I'm the parent, my child's PID is 12213, and the child said, I'm the child. Well, let's do a PS -LF. And we see 4 processes. We see bin bash, that's, you know, my bash shell that's sitting here, process ID 11694. We see that the ftest command has been run. That's this process right here. Its parent's process is 11694, that's bash. So this is the ftest that was started when I said ftest. But there's another copy of ftest running. And the parent of this process is 12.2.1.12. What's that? That's that first version of ftest. And so bash was the parent of this ftest, which is the parent of that ftest. And so we have 2 processes running. And you know, the child identified, the parent identified the child PID as 12213. That's this process right here. So this is 2 processes running independently of each other. They're executing asynchronously, I would say, because they're not in lockstep with one another. If I had a single CPU with a single core, then it would be time sharing. The first process would get some cycles, and then the second process, and then the first, and so on. I have multiple cores on the CPU, so they're probably executing at the same time in different execution cores. So it's multi-threaded in that sense, but multi-threading is a whole topic in itself. And when we talk about Java and 223 and Spring, we'll spend a while talking about process threads in particular. But yeah, I would say this is probably multi-threaded as well as being asynchronous. Now I can foreground my process and Control C it, and now, you know, both of those ftests are gone. So forks can be a little dangerous, and let me show you how easy it is to get into trouble with forks. And my disclaimer here is just going to be, don't do this, right? So let me just call fork and go to sleep. Alright, so I make a call to fork, it says done with fork, call, done with fork, call, and if I do a PS, I've got 2 copies of ftest, and I can kill those. So if I do the following, if I make 4 calls to fork, and I run my ftest, I get a bunch of output. And if I do my PS, I've got 16 copies of my ftest program. And this is easy to do accidentally. It's easy to do on purpose too, but it's not unusual that this happens accidentally. And you know, I've got 4 calls to fork, but I ended up with 16 processes. So what's happening here? I have my main program, and I'm executing, and I say fork, and that creates a clone of my program. And that clone thinks it just finished this call to fork. And now both processes are about to make this call to fork. And when that happens, each process creates a new process. And so now I have 4 processes that have just finished this statement or are about to make this call to fork. And so each of those 4 processes makes a clone of itself. And now I've got 8 processes. And each of those 8 processes thinks it just finished this line of code and is now ready to do this call to fork. And when that happens, each of those 8 processes makes a clone. And now I've got 16 processes. And each of those 16 processes says done with fork call, which is why I got 16 copies of this message. So yeah, this is exponential growth, geometric growth. And that was with 4 calls to fork, right? If I did 10 calls to fork, I would create 1,000 processes. If I did, 50 calls to fork, I would probably crash my machine, because that would require 2 to the 50th processes, and there aren't enough process spaces, there aren't enough resources to create that many processes. And when you run out of process slots, your machine is pretty much hosed. Because remember, if I want to kill a process, I have to create a new process to execute the kill command. And if I can't create processes, there's not much I can do. And pretty likely at some point, the kernel will panic and the system will crash. So don't do this on the server, okay? If you want to try this, go into your own Unix system or start a virtual machine and play around with it. And from C, it's very easy. Right, that's a fork bomb. But it's pretty easy to tell what happened after this brings the system down. Now I've tried to set up the Unix server to prevent either intentional or accidental things like this from bringing the system down. But I've also tried to allocate people enough process slots so if they want to use tmux or things like that, they can do it. So there's a chance if you do this, it'll shut the server down and people will get angry at you. So don't do this on the Linux server, but open a virtual box with a Linux system. You can play with this all you like. And if you just write a shell script called main, and inside there you make a call to main, every time you create a new process from bash, a fork is executed to create that that new process. And so, you know, this is not the same kind of fork bomb, but this will run out of process slots. But if I put this inside a loop, right, that's basically a fork bomb too. So pretty easy to consume all the resources, and not a lot of glory in it. But if you want to experiment, you know, for science purposes on a dedicated machine, preferably a virtual one, you can experiment with that. What I want to talk about next tomorrow is how we can use this to do things from C, like run other commands. And the usual way this is done is, you know, we use fork to create a child process, and then we do exec or execl to create, to change what that process does. But there's actually a nice chapter 3 system call called system that will do this for us. And system is basically a call to fork and execl, and it lets us run commands from inside a C program. And that's a useful thing to do. So we'll play with that a little bit tomorrow. And then we'll start looking at how can we run a command from C that we want to interact with. Not just, you know, print out a talking cow or something, but send information to or get information from this command. And this will take us into popen and execls and pipes and things like that. So we'll play with that tomorrow. We'll wrap that up on Thursday. Friday we'll talk about the final. All right, send me an attendance note on the way out. Have a fantastic afternoon. I will see everybody tomorrow.
Thanks.
Thanks. Have a good one.